Hello, everyone. Oh, lots of people with Kaspa shares here. That's nice. Apparently, I'm going to introduce myself, which is a pleasure because I get to say my name correctly. So, nice seeing you all here. I am Dr. Shai Wyborski, and I'm here to talk a little bit about Kaspa. It seems like most of you have already heard about Kaspa. But I hope this talk gives you a little bit more of a focus on the way I see what we're all about. So one thing that I hear people say constantly about Kaspa is that Kaspa is just another chain. It's just another L1. What does it do? What does it achieve? What is it good for? And I think my focus here, my intent here is to explain why Kaspa is indeed actually very, very unique and offers some things that no other tech is able to offer so far. So if I have to sum it up to like a few sentences, a few slogans, or one slogan, is that Kaspa is the only proof of work that is able to scale down confirmation times to be as fast as the internet, which is the fastest possible, while also increasing the throughput to be as spacious as the hardware allows, which is also the theoretical limit. It manages to remove all the security bottlenecks from the protocol and just gives you the best response times and throughput that you could hope to achieve. Like the only thing that limits it is the hardware and the network that you are running it on. So if we look at numbers, and right now we are able to support 3,000 transactions per second with very, very fast confirmation times, 10 blocks per second, where the nodes we're using are running on cheap hardware. I'm going to get into numbers a bit later. And I also want to stress out at the get-go that Kaspa also provides two other unique solutions that I don't think exist in any other technology. And one of them is unique approach to mitigating and solving actually minor extractable values, MEV. And the other one is to provide a very unique and interesting approach to fee market design and how we can offer solutions to some of the problems with fee markets that we see on current proofs of work. And I believe that once all of these things are implemented and in place and proven themselves, then Kaspa will actually be the only layer one you actually need. It could be spacious enough and performant enough and cheap enough to support all of the utility you need to hold all of the layer twos you could ever dream about putting on a network. So before I talk about what Kaspa does differently, let's talk about what Kaspa does similarly. Well, it is a proof of work. We all know what a proof of work is. There are miners and they mine, and the more of the fraction of the hash rate they have, the more influence they have on the final decision of the network, and the more money they earn. We go with the model, the UTXO model. We go with block rewards, the same incentive, at the core, the same ideas of the incentive model of how to incentivize miners to do what we expect them to do. And the security, the way we reason about security is very, I like the word Bitcoin-esque. It's the same security properties and security definitions as Bitcoin. We don't, I've seen there are several projects that can allegedly offer what we can offer, but the way they do it is by giving weak and arguably unreasonably weaker definition of what security is and what confirmation security is. And I see it a lot in zero confirmation claims and claims of immediate confirmations where if you believe that this lesser form of security is adequate, then yes, you can confirm transactions faster. But in Kaspa, when we talk about confirmation times, we mean with the same security that you would get for waiting 6 blocks in Bitcoin. Okay, so let's start with talking about the consensus layer, the core. So there are several known approaches for proof of work consensus. The most known one is by far the blockchain. And the two main flavors of blockchains are either the longest chain rule or the ghost rule. But no matter what you look at, how you look at it, essentially they orphan blocks. And because they orphan blocks, in order to be secure, you need your blocks to be sufficiently spatially separated. You need to wait enough time between blocks, and you can't really cheat this by creating large blocks, because the larger the blocks, the longer you have to wait because you increase their delay. So the result of these networks, all the classical networks, Bitcoin or pre-merge Ethereum, Bitcoin Cash, Litecoin, all of the traditional chains, is that they have low throughput and high latency. And people try to come up with all sorts of solutions for this. One example is the parallel chain blockchains, which includes protocols like BlockFlow and Chainweb and Quai. And these protocols say stuff like, the core idea is that we are going to have a few chains. Each chain operates just like a classical chain, but we somehow braid these chains together, so you can only 51 attack one of these chains by attacking all of the chains. So it's an interesting, nice approach that allows you to increase throughput, but not only that it does not improve latency, it actually has worse latency, because you don't only have to wait for the chain itself to accumulate enough confirmation, whatever chains you have your transaction on, you have to wait for it to braid enough with other chains so that you'd have to invert all of them to invert the original chain. And so it gives you a better throughput, but it actually makes for worse latency. Another DAG-based approach is the summary blocks approach. And so some famous examples are fruit chains and Prism and Tailstorm. And they essentially say you can create a lot of blocks and you can have a lot of parallel blocks. And these blocks contain information, but they don't really contribute towards accumulating the security of the transaction, not reverting. Every once in a while, we are going to have these summary blocks that takes everything below them and say, okay, we are now ordering this, we are deciding what's the consensus at this point of this block. And since this block is not going to revert, if you're waiting it to have like 5 or 6 summary blocks above it, you get this nice property that you get all of the throughput and you get latency that is similar to traditional chains. So it is an improvement, but it's not quite there yet because the latency is still determined by the security of the protocol. You still need the distance, the time between two summary blocks to be high enough so that you won't get much of them in parallel. And before you see these summary blocks, you can't really confirm a transaction. And there are other based protocols, DAG-based protocols, like Conflux and Tangem. And the main point for these protocols is that they take this DAG and they try to sort it in like a ghost-like way. They say, if we have a conflict, then you would like to choose the side that has more weight above it, like a larger future above it. And this works when you are working on chains. But when you move from chains to DAGs, the problem is that very soon after the conflict, both sides of the conflicts are published, then all new blocks will add weight to both sides of the conflict. So the difference between one side and the other doesn't continuously grow like it is when you are limited to chains. And this picture kind of tries to illustrate this, where if you count, you will see that of B and B prime, B actually leads just by one block, even though quite a lot of blocks have accumulated. And an attacker can just post these two red blocks, and suddenly they can switch the consensus. And they can keep doing this, no matter how long have passed. And this is what we call the liveness issue, which arises because of the fact that Ghost looks at the future. And if you look at future blocks, then all of them, but just maybe a little few, will add weight to both sides of the conflict. They don't get to choose which side of the conflict they prefer. And now Ghost DAG, despite the name, is a Bitcoin-like consensus. It's not a Ghost-like consensus. In a sense, it looks to the past. When you have two sides of the conflict, the past of the blocks containing these two sides is the one that decides which side is winning. So it becomes cemented very fast, and then you can't affect it. When any block that sees both sides of the conflict and is passed doesn't affect the decision in any way. So it gives us, I'm not going to go into how the protocol works right now. There are a lot of videos and explanations online. But the fact that it applies to DAG like a longest chain rule kind of approach and not a ghost kind of approach is what allows us to create this thing that confirms very, very fast and doesn't have the liveness issues. So this is like what gets all of the pieces together on the consensus layer and gives us this unique instant confirmation property that was proven to be false for all attempts like this before because of the ghost-centric view that says, let's look at the future, because looking at the future in DAG contracts doesn't really prove itself. So this is, in a nutshell, what Kaspa does differently on the consensus layer. Now, how about running a node? So if we look at most chains, we see this thing that we've learned to take for granted, that each chain keeps a copy of the entire history of computation on each node. If you want to verify the node, you need to have the entire history. Either that or you need to have some snapshot that you trust. And the result is that storage requirements increase with time. And the only way to really mitigate it is if you have like very low throughput systems like Bitcoin, where even though it increases with time, it increases slowly. But even then, we see that syncing a Bitcoin node can take up to a week. So something here is still kind of weird. And people, not us, actually it was realized before us by KAS, Zindros, and Leonardis, that you can use something called the MLS, mining in logarithmic space protocol. You can provide what they call the non-interactive proof of work, a NIPOPO, that replaces the need to store the entire history. Instead, you store a very small proof. We took this idea and we adapted it to DAGs, and we added to it another novel protocol we invented for pruning the block data. And as a result, we get security that is similar to Bitcoin, but the amount of storage remained fixed. And the result is, one result is that even when we are working in the full capacity of 3,000 transactions per second on the testnet right now, we see that in the latest version, it takes 20 minutes to sync a new node. Another issue is the validation costs. This is more of a painful point for proof of stake because BFT in all of its source is not very efficient. Even the most performant BFTs, if you want to run high throughput through them, you find, for example, in Solana, that a validator requires hardware that costs about $10,000, and the utility costs, even just replacing hard drives and electricity and the hardware maintenance, it comes up to about $400 a month. In comparison, our testnet that is running right now on 3,000 transactions per second, people run it on like 10-year-old laptops, they run it on Raspberry Pis, on old cell phones, and the operational costs are completely marginal. So this is like a unique benefit of proof of work. Proof of work is much, much easier to validate than proof of stake. So this is a huge benefit of having a proof of work which gives you the performance of proof of stake. It remains much more decentralized because validating it doesn't matter what the rate is, validating is just checking a hash and see that it nonces right. It's just very, very cheap check. Another issue is the problem of state bloat. Essentially, as the network runs, it accumulates more and more addresses that has a balance, and this is in the UTXO world. In the smart contract world, you have all sorts of storage, and it becomes very hard to limit and track how much storage is required to keep the state of the network. Now I'm not talking about the ledger, just about the current state. There are several solutions that exist today, and each has their own drawback. Some networks like Bitcoin, they keep the entire state. It just means that as it bloats, you need more storage. Other approach is demurrage. It's just saying if you haven't moved money for a long while, then it starts to devalue. And I think this just undermines the entire concept of crypto, that once you have money, you have it forever and nothing can take it away from you. Sharded states is also a solution that exists in some forms, which causes huge data availability issues. And another approach is stateless clients, which seems promising. It uses this cool cryptographic trick called accumulators, which allows you to have this huge data set, but represented very slowly, very succinctly, and you only give proofs to the holders. But there are two problems with it. One is that as of today, we don't know how to do it in a way that as we add more UTXO, we need to update back old witnesses. So clients need to stay online and update their proofs. And worse than that, you can't derive the proofs from your seed because the proofs depend on the current state. So it's completely incompatible with stuff we all take for granted today, like HD wallets. So in Kaspa, this guy over there, Michael Sutton, he came up with a completely new way. What, I ruined the surprise? He came up with a completely new way that we call the harmonic storage mass. It's just you very, very cleverly decide what the weight of a transaction is according to its inputs and outputs, and you automatically get this magic property that no matter how you perform your attack, the amount of block space that you waste is quadratic. It's the square of the amount of storage that you wasted. So either it's because of throughput or because of fees, the attack becomes unfeasible very, very fast. If you Google KEEP 9, KEEP Kaspa Improvement Proposal 9, you could see a lot of hard numbers and analysis of this very, very nice technique. And KEEP 10 also explains how you could very, very gently expand the UTXO model a bit to have great support for microtransactions in this model. Okay, so some numbers about our performance. As I said, on the mainnet right now we have 1 block per second, 300 transactions per second. The testnet is live, it's open, anyone can join it, anyone can spam it, do whatever they want. We are running on 3,000 transactions per second, over 10 blocks per second, very, very smoothly. People join, again, as I said, with very cheap hardware. People sync old cell phones to the mainnet, the testnet, and still they are holding their own, and the nodes are holding 3,000 transactions per second without even breaking a sweat. And we believe we can go higher. I believe we can go over 10,000, but right now there is no need to. And in the following few months, we are going to have the Crescendo hard fork, which is going to introduce a lot of changes and updates, including increasing the block rate to 10 blocks per second and the TPS to 3,000 transactions per second on the mainnet. It's just around the corner. On the 15th of September, we had the KRC20 launch. KRC20 is a platform for tokens, which is very similar but also very different from the Bitcoin's BRC20. So I'm not going to talk about the KRC technology itself. It's interesting, but it's developed by an independent team called Kasplex, which are awesome, and you can check them out. But the point is that the launch of the KRC was the biggest live experiment in the history of proof of work. About 100 coins were minted on the same day, and people created transactions in rates of like 600, 700 transactions per second. The mempool queues went as up as 250,000 transactions, and over 20 million transactions were processed in 24 hours. You can see a few graphs here. The left graph is the graph of the transactions per block, and above you can see how this compares to other coins and the most transactions they have processed in 24 hours. Never before in the history of distributed computing has a decentralized system managed to process these many transactions while all of the nodes of the network ran on 100 buck machines, and we had no outages at all. So I think the KAS 20 launch in itself is a historic event that more people should be aware of. Okay, the next thing that makes Kaspa unique is that development is completely community-based. Other coins, a lot of coins, in order to fund their development, they're using dev fees or VC-backed development, or foundations that were created by the original team using some share of the coin. In Kaspa, we really believed in a if we build it, they will come approach. All of the funding was, all of the development was funded by the community, initially by funding pools and now by foundations like the Kaspa Ecosystem Foundation and the Kaspa Industrial Initiative. And as a result, the dev teams, even the very original devs, they have to consistently prove themselves to the community. And another result of that is that people keep joining and contributing. And this map shows the core developers, or the developers that only work on the Rusty Kaspa code base. And even though it started with a few devs from Israel, we now have 21 contributors from, I think, 17 different countries. So this really makes the project very global and decentralized in its development. I'm going to speak faster because I'm running out of time here. We also had our fair launch. As we say, no pre-man and no allocation. And also the mining algorithm itself was chosen a day before the launch, so no one would have an advantage. And this is also talked about in this subject of decentralized mining. A lot of people think that Kaspa mining is centralized because of ASICs. But I believe that the only way to be truly decentralized is by being ASIC friendly. Because ASIC resistance is kind of a myth. It's just temporary. If your coin will become valuable enough, designated hardware will win. And then because you went with an ASIC resistant algorithm, the designated hardware will still be more expensive to produce, to buy, and to operate. So you ended up losing on both sides. On one hand, only designated hardware dominates your mining, but on the other hand, it's expensive and it's not accessible to a lot of people. In Kaspa, we used a very ASIC-friendly algorithm, but we modified it so that existing hardware couldn't mine it yet, and we made rapid emissions, so by the time ASICs hit the market, most of the coin have been mined by GPU miners, which have a lot more operational costs, so they sell much more of the coin. About 65% of the coin was mined before ASICs emerged, which is similar to Bitcoin. And we see that because of the higher BPS and higher TPS, it's actually much, much cheaper to get a meaningful share of the mining. So, for example, Bitcoin, the current capital expense of all Bitcoin mining is around $12 billion. And since Bitcoin mines about 1,000 blocks a week, it means that if you want to see revenue once per week, you need $12 million of initial investment. If Kaspa CapEx was as large as Bitcoin, the whole 12 billion, since Kaspa produces 6 million blocks a week, if you want to see a weekly revenue, the initial investment you need to put in is only $2,000. So this means that mining is much more decentralized. And as a result, we see that even though there are large mining machines, the small home mining machines are still the most popular. I wanted to say something about fee markets, but I don't think I have a lot of time left. But the key point, and I encourage you to look it up, is that because there is a lot of parallelism, miners who want to maximize their profits are incentivized to apply some randomness to how they choose transaction, and this has two very cool effects. One is that incentives to pay fees start to emerge long before the network is congested. And the other one is that transactions are not starved. If you pay low fee, you won't starve forever, you just wait longer. So the upshot is that we have a much healthier fee market where the fee you pay represents the quality of service you expect to get much better. And so this is what these slides are supposed to say. I'm really running out of time. I'll just say that the parallelism also allows for some really cool MEV resistance that is not really possible without them, because this whole very, very high throughput, high parallelism actually means that when a miner creates a block, he doesn't have perfect information about the present, and this could be used for miners to compete for the privilege to include transaction, and then they will naturally share the extracted value with the user, which is like the only solution I know of that is able to achieve that. Okay, so my time is up. There is so much to say about smart contracts and how cool they're going to be on Kaspa, and how they're going to give you the best of both worlds, and how, because Kaspa is so fast, you can do the entire validation on-chain with this unique MEV resistance and still get responsiveness as though you are doing the sync off-chain. But I don't have time, so I won't say it. So I had a whole lot to say about what we are going to do on the layer 1, on the layer 2, but you will just have to either review this video and pause or look up our website, because I talked way too much on the first part. But that's it, pretty much. Thank you very much. And thank you all for coming, and thank you for the support. Thanks for Nexa for sponsoring this nice venue. And thank you all, guys. I love you.